Good morning, students. Yesterday, I conducted class with you and began with the chapter solid state. So I'll quickly recap all that we did yesterday, and then I'll take it ahead so that we complete this chapter. So that the coming week when we meet, we do some numericals. Okay. So what I'll be doing is I'll be sending you the notes. As I mentioned in the class, I'll be sending you the notes. I expect you to go through them, and I'll be sending you the question and answers from the exercise, which I expect you to write down in your notebook. Okay, so let me quickly recap this chapter. What we did was we did the introduction part of solid state, and we looked at the classification of solids, right? That solids are classified into two types: crystalline and amorphous. Okay, so we looked at the distinguishing points between them, between crystalline and amorphous solids. We looked at isomorphism and polymorphism, and then we went on to look at classification of crystalline solids, right? So there are rather four types of crystalline solids: molecular solids, ionic solids, metallic solids, and covalent solids. We looked at them individually, right, and tried to understand on what basis these solids were classified. Then we looked at the meaning of the word crystal, the meaning of the word lattice and basis, right? And then we came down to find out what unit cells are. Okay, so the smallest repeating structural unit of a crystalline solid is called a unit cell. Okay, so I also made you uh, understand what is this letter A, B, C. They're called as edge lengths. Okay, and then there are angles. Okay, which are caused due to those edge length, that is alpha, beta, and gamma. And then we went on to see different types of crystal systems, or rather unit cells. SCC, that is simple cubic cell. Then there is BCC, that is body centered unit cell. Face centered unit cell, that is FCC. Okay, so I explained this picture to you to help you understand how many atoms are there in each type of unit cell. So in SCC there is one atom, and that comes from the very fact that there are eight atoms in eight corners, so there is 1/8 of that atom contributing. Okay, so 1 upon 8 into 8, you get one atom. Similarly with BCC, it's 1 upon 8 into 8, that is one atom plus one at the center of this body, so that makes 1 plus 1 equal to 2. And the face centered cubic cell has got in all four atoms, one from the eight corners and three from the faces. Okay, so that's how you get four atoms in FCC. Then we looked at the crystal systems. Okay, that is, there are 14 lattices, uh, you know that was brought in by Bravais. Okay, so these were the 14 Bravais lattices that we looked at. The only difference between all these 14 is, or rather not 14, but uh, they are divided into cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral. Okay, so the difference between all these is in their edge lengths and angles created by those edge lengths. Okay, so this is something that we had already seen regarding number of particles in cubic unit cells. SCC has got one particle or one atom, body center particles, and face center is four particles or four atoms. Okay, per unit cell. We also looked at the relationship between molar mass, density of the substance, and unit cell edge length. So eventually we got this formula, a very very important formula: density D is equal to Z into capital M upon A cube into Na, where Z is what? Number of atoms in a cubic cell, multiplied by capital M, which is molar mass, upon A cube, where A is the edge length. Okay, and Na is the Avogadro's number, which we already know. Then we came to packing. As I mentioned, my dear students, in the class, that a sphere always uh, creates some kind of a gap. So more uh, the packing of a substance, stronger is that solid. That's why packing is a very very important criteria in any solid. Better packed substance, more stronger it is. Okay, so while we were doing this, I also took you through coordination number and the magnitude of the coordination number. Then we looked at this diagram, wherein these gaps between two atoms, okay, they're called as depressions. So depressions, basically they are the ones which are responsible for creating voids that we'll come to know later. Now coordination number for a square close packing will be 4. Okay, basically coordination number is what? It's the number of atoms attached to the central metal atom. Okay, so for a packing like this, the coordination number will be 4. For a packing like this, that is hexagonal close packing, the coordination number will be 1, 2, 3, 4, 5, 6. Okay, and so on. So this is something that we had seen. Okay, and the voids that are created, if you remember, my dear students, I did tell you voids are important uh, things to study in solids, because they are the ones which help us to understand whether the solid is going to be weak or strong, and how those voids can be filled. No, so there are two types of void: one is tetrahedral void and octahedral void. Now we will go ahead. So we stopped at octahedral void, and then uh, we ended the class there. So we'll just quickly continue with the packing efficiency. So all this while I was telling you why packing is important. So at the same time, we need to also understand the efficiency of packing. No? So like the coordination number, the magnitude of packing efficiency gives a measure of how tightly particles are packed together. Okay, so packing efficiency is nothing but the fraction or a percentage of the total space occupied by the spheres. Okay, so I'll just like to give you an example. The meaning of the word total space occupied by the sphere, which means if more than number of spheres in a unit cell, okay, or in a cube, okay, better will be the packing efficiency. So if I ask you, out of SCC, BCC and FCC, which unit cell will have a better packing efficiency, you will say the answer is very very simple: FCC. No, because FCC has got more number of atoms in that unit cell, that's why there'll be less empty space. On the other hand, SCC will have lot of empty space. No, so that's why its efficiency will not that great as compared to BCC and FCC. So the formula that is given to find out packing efficiency is volume occupied by particles unit in unit cell upon the total volume of unit cell into 100. So that becomes the packing efficiency. Okay, so let's take a look at packing efficiency one by one. So we'll begin with simple cubic cell. Okay, so in this simple cubic cell, this is how the simple cubic cell looks like. Okay, from front, we all know that it has got 8 atoms in 8 corners, right? That's what we know. Yeah, so a face of a simple cubic cell is shown in figure given below, so that is over here. So it is evident that edge length A is twice radius. No, so this is the edge length. So something like this will be drawn here. No, so this is the cube that is formed. So only this 1/8 part contributes towards where my cursor is. So you'll see only the 1/8 part is contributing. Okay, so therefore the radius is what? Edge length upon 2. So if I have to find out volume of the unit cell, which is a cube, okay, so in terms of radius it becomes 8r cube. Okay, so it becomes 8r cube. Remember, what are the things that I need to find out packing efficiency? I need to know volume occupied by particles in a unit cell and total volume of unit cell. So in this case, in the first step, I was able to find out volume of unit cell, which is 8r cube. In the second step, we'll find out volume of the sphere. Why? Because each atom present in this unit cell is nothing but a sphere. So what's the formula for a sphere? Volume of one sphere will be what? 4 upon 3 pi r cube. Okay. Now the third step would be what? Empty space in unit cell is nothing but total volume minus volume of one sphere. Now why am I taking one sphere or one atom? Because in a simple cubic cell, there's only one atom, correct? 1 upon 8 into 8, which is equal to one atom. Therefore I put total volume from step 1, which is 8r cube, from step 2, that is volume of one sphere, as 4 upon 3 pi r cube. the empty or unoccupied space is called void. Okay, so the empty or unoccupied space is called void. What will be step 4? Packing efficiency. So since 8r cube is the volume occupied by entire cell, let's assume it as 100% occupancy. However, volume occupied in SCC is 4 upon 3 pi r cube, which is volume of one atom. Thus, 8r cube is equal to 100%, 4 upon 3 pi r cube is equal to x%, where x is the percentage of volume occupied. So after cross multiplying, we get volume occupied x is equal to 52.36%. The remaining 47.64% is the volume unoccupied, or it is void. So you can imagine, my dear students, almost 50% of the space which is there in SCC is unoccupied, right? That's why SCC type of unit cell is not very strong, because there is lot of unoccupied space in it. Okay, so this number you'll have to keep in mind. The packing efficiency for SCC is 52.36, a potential MCQ type of question. And the remaining is 47.64%. How will you find out remaining? You just have to subtract 52.36 from 100. So you get 47.64. In the same manner, we'll find out for BCC also, body centered cubic cell. Now in this case, total volume of the cube is dependent on value of R. Okay, so in BCC, in body centered, the edge length A is equal to 4r upon root 3. Remember, in SCC it was 2r, but in BCC, why there is it's 4r upon root 3? Because the edge length is also needs to be calculated. What needs to be calculated is the atom at the center. Remember, in BCC there is an atom inside the body. Okay, so that's why edge length considers the radius of that sphere also. That's why edge length A becomes 4r upon root 3. So therefore the total volume of the cube is equal to A cube, which is equal to 64r cube. 4 cube is how much? 64 r cube 3 root 3. Okay, now in step 2, since BCC contains two atoms, correct? In body centered, how many atoms are there? Two atoms. 8 at 1/8 into 8, which is equal to 1, plus 1 at the center. So 1 plus 1, 2 atoms. So volume occupied by the atoms in BCC type unit cell is equal to 2, because there are two atoms, 2 into 4 pi r cube upon 3. Now this 4 pi r cube upon 3 has come from where? It's the volume of the sphere, which we also considered in this case, 4 upon 3 pi r cube. So same thing we are going to see over here, 4 upon 3 pi r cube. So volume occupied by the atoms in BCC type unit cell is 8 pi r cube upon 3. So now that I know total volume of the cube, now that I know volume occupied by the atoms, very simple to find out packing efficiency. So 64 r cube upon 3 root 3 is equal to 100%. That is, this is if it is 100% occupancy. 8 pi r cube upon 3 will be the volume occupied. Okay, which also becomes our packing efficiency. So after cross multiplying, we get volume occupied x equal to 68%. How will you cross multiply? You will just take this x that side, you'll take this that side, and get all these things on the other side. So you get 68%, and the remaining becomes 32%. So clearly you can see BCC has got better packing efficiency than what we saw in SCC. SCC at 52.36, BCC has got 68%. Okay, similarly, the packing efficiency in face centered cubic cell. Okay, so A is equal to r root 8. So here A cube becomes 8r cube root 8. Now since there are 4 atoms, we multiply 4 into 4 pi r cube upon 3. Again you cross multiply. So after cross multiplying, we get volume occupied x equal to 74%. The remaining 26% is the volume unoccupied or void. So clearly you could see, my dear students, FCC has got a better packing efficiency as compared to SCC and BCC. So quickly let's take a look at this. So coordination number of atoms in SCC is 6, in BCC it's 8, in FCC it is 12. Okay, so packing efficiency is also given over here. So in this video, my dear students, I just wanted to take you through packing. I'll be sending you some more videos also to do the other parts of this chapter.